So up next, we have Mr. Prasad. He's the CEO of HitDime.com, a cloud analytics service that's owned by Lead Semantics, a semantic big data analytics company founded by Prasad. He's based in Hyderabad, India, and works closely with his technology and business partners in the US. Previously, Prasad founded a telecom analytics company that developed and sold a career-grade analytics appliance built with COTS hardware, a first of its kind in 2008, offering petascale network data mining and analysis at $1 million price. So please join me welcoming Prasad this afternoon.
Thank you. Yeah. Am I audible? Yeah, is that on? Yeah. Well, I think I can still say good morning. We are probably late in the morning towards the afternoon. So good morning again. My name is Prasad Yalamanchi. I am founder CEO of Lead Semantics, a semantic big data company out of Hyderabad. We have recently released a cloud analytics tool on the web. I'll probably have a chance to show a 2-minute version of it later on in the demo. It is relevant being that it uses semantic technology, and the topic today is smart big data lake. And before I get going, I would like to request with a show of hands, how many of you here have heard of data lakes? Quite a few, and if I can get the count right, it's probably about 40%, I think. That's quite a good number. How many of you think data lakes are real and not a mere concept? Okay, that's very good too. Now, one more couple of questions again. How many of you heard of semantic technology? Little lesser, but I'm very happy that there are at least 20%. It appears to be 20%. Yeah. And how many of you think semantic technologies are real and not mere concept? There are a couple. I'm very happy. I mean, it's probably 3-4%. I would add to that. So hopefully, in my talk, I'll know where to focus. I'll try and give you a little bit of an insight as to why semantic technologies are real, and most importantly, they solve a very important critical problem that's kind of tagged with data lakes. Yeah. So before we get going, excuse me, which is it? No, the slides. Yeah. Okay. Great. So it's smart big data lake, and the tagline is, make big data lakes deliver analytics today. And hinting in the tagline is that data lakes are not delivering on the promise, what you would normally expect. So I'll start off setting the concept with, where all this analytics situation has begun. Analytics over the last several decades, I mean, maybe 2 or 3 decades, data warehouses have been the mainstay of delivering operational analytics to the, enterprise organization. More than 80% of the enterprise analytics users get their operational analytics through data warehouses. And these data warehouses are predominantly, they handle structured data, they compute and, one way or another generate all these multi-dimensional views through BI and visualization tools that, all of us have grown very familiar with. And they're, being that they have been around for the last 2 or 3 decades, as we said, the mature practices of governance and things like that have kind of led the entire analytics to be, you expect higher quality out of this entire pipeline. So they have a role to play even in all this changing world. But given the situation that, they deal with majority of the time structured and, relational data, and when you put it against the context today that we are in, where, majority of the data in the enterprise is beginning to be unstructured. It is so unstructured, it's getting to be more than the structured data. These data warehouses, these venerable data warehouses that have really done their job for so long, seem to be inadequate in this new context. So what do we do with that? So this new world is the new world of big data. And the way it is characterized is that the new data is like the social, the photos and, the log data, which is like enormous. I mean, we know that log data came out of nowhere, and the amount of insights that, people glean out of this log data analysis is mind-boggling sometimes, security particularly. and the call center data, I mean, on and on, geolocation data, that's kind of, again, in terms of volumes and, the types of data that it throws up are different and, something that you cannot handle it through data warehouses of, the previous decades. And the scale, all of this has, this is no news to you guys, given that, the confluence of the big advancement in automation, in data collection and, all this data center, computations and, all this stuff have led to this, the scale of, data being collected, processed and, now to be able to generate insights out of that, you would need to do analytics with this big data and over and beyond the, data warehouses that we are familiar with. So all this, data that is being, analyzed, it's by these new age techniques like machine learning, graph analysis, social network analysis, I mean, all of these interesting things. All these things are being done by very expert, highly skilled engineers and scientists in the organization. And typically these analyses are kind of directed towards a smaller group of, folks inside the organization. As we said, operational analytics still is the main staple, and that, predominantly serves probably about 80% of the analytics users, right? And so this big data analytics serves a smaller group, but these are high value. They're pointing to kind of, very important directions that the company ought to take. And these things are delivered to the users through very special one-off kind of, user interface, because, old world BI visualization tools did not have a place for these types of, user interfaces that can cater to the new analysis. So only now recently, like for example, over the last couple of years, we have been seeing that, the yesterday's BI and visualization tools have started adding interesting plugins and add-ons that require considerable, configuration and setup and so on. It's not natural, they were not organic. So it looks like there is some, some room for new players to come in and, add in new tools there. And the other thing that we are seeing is that, as you all have seen, at least 40% of you are already aware of data lakes. Current scenario in big organizations, some organizations for sure, there are multiple big data clusters. Each of these clusters kind of, doing this high-end analytic, for example. Like, if you have a graph analysis that's trying to kind of, get you new insights into the data, then there is a cluster of big data that is kind of set aside for graph analysis. There is another big data cluster that is doing, social network analysis, for example, and machine learning for sure. Things like that. So within an organization, you are ending up with multiple big data clusters. So you need a new level of abstraction to kind of handle all these, different clusters. This is at a different scale. And that is where, we are coming into the term called data lake, as experts call this, and they characterize big data lakes as, a single point of ingest. When you are dealing with these additional sources of data, like Facebook data, Twitter data, log data, and all of these things, these are individually different sources. Each of them at the ingest point will be done very little ETL, so to speak, so as to retain all the, the provenance and, the traceability to the source. So each of these additional sources will have a place in the data lake, and this would be one single ingest point. These are the two characteristics of the data lake. So for example, in an organization that has a data lake, all the input sources will have individually defined spaces there. You can actually locate them. So each of these things, is a different source. Like you have video and movies and things like that. They will all end up actually finding a identifiable spot in the lake. So now what happens? Because there is very little ETL done, when a data science team comes up with a wonderful new analytic that they want to calculate with this input data, they will have to kind of, promote a project that ends up having to do the ETL necessary to bring in all this, pieces of data from all these sources, towards a target schema specific to that analytic. So all that exercise is kind of deferred. It's kind of late binding, so to speak. So that work is not going away. It seemed kind of, pretty interesting at the, on the upfront, saying that, you are able to collect all data into the data lake, but the work necessary for individual analytic is still there. And it is now thrown on the backs of, the data scientists who are normally skilled on, very valuable other things that we talked about. So that is one of the other things that need to be sorted out. And the other important thing is that, being that this is a newer concept, the governance that we are so familiar with the data warehouse world, that is still evolving. The governance that kind of, talks about security and access controls, and all those, curation of data, for example, all these things are very important things so that you can promote quality and expect quality on the other end of the pipeline. So that is still in the, still evolving. So the important thing is the benefit of, at least, we should not, write off these, data lakes. They are wonderful concept. It is a higher level abstraction. It, it gives you a chance to kind of do schema and read, so to speak. I'm sure, most of you all have heard about it. What it does is, on an analytics specific requirement, you are able to apply the new schema on this, input data, be it from multiple sources. And you have the flexibility of doing, different types of analytics that way. So the promise is there, but there are certain, logistical issues and, the management issues that need to be sorted out. So where are we now? What can we do about it? We are in that phase as where we view it. We are in that phase where things need to be sorted out. And we have in summary of the data lakes, for example, the data scientists are well dressed and all that, but it seems like, this is the wrong situation to be dressed up like that. He looks like he needs to paddle a long ways before he gets a clear lake, because it is unwieldy and inefficient at this point, because being that, the repeatable steps of, pure science or reproducible results is not to be, not to be had at this point anyway. So what we think is, and what should we do to this data lake, which is a wonderful concept, and we look to Gartner, good old Gartner, they set the direction. They say whenever you are trying to meet, needs of a wider audience, it is good to have curated repositories. Of course, we all know that even from data warehouse times. You need good governance and you need good access controls. And additionally, what they talk about is you need semantic consistency, and that is the new thing that has been touted by Gartner. And to do that, being that our world, our experience, our viewpoint is all, semantics, we think, making the data lake smarter is the way to go forward, and we can actually deliver analytics, as hopefully I'll make the point going forward. So what is making the data lake smarter? To make it smart, we have to use semantic technology. And what is semantic technology? Semantic technology, unlike the previous technologies, it relies on one very important thing. Within the semantic world, when the data is coming in, all data is uniformly encoded. And this uniform encoding is required by specification of the standards, whatever, that was set. And before I go further on this, I would like to just draw your attention to the pyramid on the right-hand side. It's very colorful, but most of you all probably are familiar with this intelligence pyramid. In computing systems, you collect data, raw data without any meaning or anything. You apply meaning, it becomes information. So it starts to kind of, make sense for whatever the purpose that you want to do your, computation, for example. You apply context to that, it becomes knowledge. And before you get to wisdom, when you apply knowledge, your wisdom is something that, is what you are after anyway. All analytics exercise ultimately is to deliver automated wisdom. That is like the holy grail of, trying to get into AI and all of this machine learning and so on. So the higher you are in this pyramid, the more efficient you are, because you are closer to the end goal. And as we said, semantic technology, what it does is, by insisting that all data that is coming in to be uniformly encoded, it raises the level of computation. It almost makes the algorithms understand the data coming in, which means it is making computation with meaning, which means you are higher up the stack. And how it does understanding, I can explain it to you. In a crude way, maybe it will make sense. All understanding for practical purposes, when you run into a new concept, new data, whatever, you feel like you understood it when you try to compare it with what you know already. And vis-a-vis what you know, comparing it with what you have seen, you judge for it, whether it is right, wrong, or whatever it is. That simple thing is what really leads to this enormous advantage in efficiency. And so within the first step itself of data ingest, you got all the data with meaning encoded and uniform, and there is no more ETL required after that into the data lake. And this is just at the ingest itself. And that is the first step. And there are many successful implementations of semantic technology. They may not be as commercially well known in other areas, but significant systems, as complicated as whatever you may be familiar with, in defense and intelligence and financial services and research and, go on and on. For example, in financial services, in the US, citizens when they file taxes, they go through like automated, audit through semantic technology solutions. And they tag these things if they kind of, go past the threshold in terms of requiring further. They were aggressively pursuing standards for semantic technology, which is unlike, the SQL or, relational world. What you have now is there are fantastic standards at each level of significant computation in moving raw data to your, whatever the end goal in terms of computation. You have data encoding as RDF, which is standardized. You have schema language, which is modeling language, which is OWL in this case. It's web ontology language. It's equivalent to your relational schema. And then there is a query language, which is Sparkle, which is equivalent to your SQL. So with these three standards in place, now all vendor systems that, sell their wares in semantic technology, you don't have to worry as a buyer. You could buy it from one vendor, have your data in that vendor's, whatever the software, and still continue to, add in new vendor systems to your system while leveraging integration and, moving data from, vendor one's data, whatever the software to the vendor second software. So without regards to any loss of information, meaning, federation, all of that stuff at runtime. So that is a wonderful thing to have when you are, trying to latch on to something big. So with the core standards in place, like, RDF, OWL, and Sparkle, I'll just get into a little bit of a detail in terms of what RDF is. RDF is like storing every bit of atomic information, attribute, so to speak, in the relational world, in the form of a triplet. It has three constituent parts: subject, predicate, and object. For example, Bengaluru is located in Karnataka. It reads, as it, meaningfully. There is no more, argument there. Karnataka is located in India. So that is the information that you want to encode. And the RDF stipulates that you use URIs, which we are all familiar with, being in the browser world and web world. These URIs are uniquely identifying what Bengaluru is. So when you see a long string of those, geonames, toponyms, # Bengaluru, there is no ambiguity. You know what you are trying to say. When Bengaluru comes in through Facebook channel or Twitter channel or somewhere else, you can at least judge which one is what you want to go with. And there is no ambiguity. And software systems can easily make that judgment for you. And similarly, Sparkle query language here. Like if you are trying to get 50 concepts from DBpedia, the query would read like select distinct concept where concept and limit 50. It's very easy to read, and you can draw parallels to SQL right there. And for ontology, which is the schema, I'm just, I don't expect you to read and follow it, but this is wine ontology as specified by W3C. So if you are in a business of wine, or if you are, connoisseur of, drinking wine, red wine or whatever, you need just these concepts, well modeled. So if a business is operating in wine, these terms, if they engage in collecting information in this fashion, there is no ambiguity. You can easily reason out. And why I say that with little more emphasis than in the relational world is, the concepts are these, the nodes, as you see, and the arrows between these nodes are the predicates. We have seen in the triplet, subject, predicate, object, right? The middle one is the predicate, and the arrows here are the predicates. But this is the predicates in the ontology level. Unlike in a relational world, you have far richer, possibilities for how you define your predicates. Like in the relational world, I'm sure there is an entity, a subclass maybe, and then there is a relationship and so on. Whereas here you have sub-properties, there are transitive properties, there are on and on, So all that are required to kind of disambiguate your understanding of the conceptual world of the domain that you are working with. The more you model it, the easier it becomes for your transactional systems. You can easily validate it. You can reason about it. So it seems a little more complicated, but of course that is a different phase of work. But once you do that, rest of your operating systems can be a lot more easy and verifiable and easy to kind of add in complex applications. So now, given you have standards and you have modeling languages, all of that in place, how do you apply it to EL? And it all gets uniformly encoded, and the data comes into the data lake. And what does that do? What it does is, the data that comes in automatically resolves for all the common nodes, which means it ends up becoming a big graph. It is an RDF graph. When you have a graph, it gives you a lot more mechanisms to kind of navigate, understand the context better. It also retains all the formats, the lineage, all of those things. Whenever you, for any particular source, if you want to encode more data, for example, you want to encode that, this was collected on a so-and-so date, and which is not part of the data that you have received, you can encode it as another triplet and couple it with the data that you are actually storing into the RDF. So all of that information in one single ingest can be collected without loss of any, meaning. And it all becomes a graph right after the first point itself. And it retains, it not just retains, it kind of, literally opens up the schema-on-read possibility right after the first step itself. And when I say schema-on-read, the data points that you receive are individual atomic units. And so whatever the filter, whatever the schema, whatever the application that you want to do, be it machine learning, graph analysis, whatever, the complicated stuff, you have a way to kind of impose that view on top of this atomic graph, so to speak. And the other important thing, as we said in data lake, it is very hard to have governance at this point. I know it is evolving, and I'm sure, there are ways to get there in time. But here, you get that governance also as another layer of ontology. Another layer of ontology that is added to your, schema model, which is the primary domain model. Much like if it were a data lake for wine set of data, you would have that wine ontology, right? And for the sake of governance, it would be another version of ontology targeted at whatever the governance attributes that you are tracking. It, of course, we expect with the governance all the good things like security and, access controls and so on and so forth. It allows for curation, and particularly in RDF, it is dynamic. For example, you get a new version of data load that you think ought to replace the prior versions. It is very easy. It's very easy. And so those kinds of things at scale will give you enormous advantage in terms of moving forward down the pipeline for analytics. And the single query, it exposes Sparkle, and as we talked about it, it's a standard. So the single query system can now ask all kinds of questions of this RDF graph. And that allows for, the analysts to kind of, come up with radically exciting new possibilities for their analytics. Whatever the domain, like, in machine learning, you can, you typically, segment out some piece of data out of this big mass of data lake, pull that out and, do your machine learning, for example. You can apply respective queries to pull that data out. As simple as that. The data scientists need not do any more of ETL like in the old data lake world. That is a significant advantage because data scientists ought to use their skill and technology and, learning in doing data science, not ETL. So that's one of those big advantages. It elevates the computing, as I said. And it also leads to one very interesting prospect. It actually leads to self-service analytics. We have been hearing literature recently on the web. There are a lot of articles that are written about self-service in the cloud analytics and so on. Now, this is a wonderful layer on which to kind of, really start planning those kinds of things. And because this is a graph of atomic all data that is all interconnected with meaning, provenance, everything in place, and with a standard query language, now we are allowed to make queries. All you need is a text interface that connects, your query back to the graph. Of course, you have to have your semantic models and, all that, which is the schema and such. It may be a little more complicated than, what I'm making it look like, but there is a very clear path. So as the big data becomes smart, how you actually, get to that end goal of, delivering analytics. First, as I said, you have to do the semantic model. Semantic model is like, when you are having, 10 different data sources for your entire business, for example, for this unstructured data handling, let's say. You kind of harmonize the meaning across all these sources. So you are going through that phase of, bringing it all together. And there are support mechanisms in this, seemingly newer field there are established mechanisms like vocabularies and taxonomies which disambiguate, when you are sitting around, all the analysts sitting around trying to, hash it out, what should be the right meaning. You have support from these standard things like, what a word should mean. You have support from taxonomies, you have support from vocabulary, so to speak. Like any given segment, like there are ontologies for defense, there are ontologies for education, so on and so forth. And there are a lot of research organizations, institutes, they publish these ontologies on the web. And so you can take advantage of those things that you didn't have to, spend money to develop. And the other thing is that during the ingest, as we said, ingest is a very critical, interesting, exciting phase. You do the mapping and transforming, applying the semantic model. And that adds the input data to the RDF graph. And so RDF graph, the basic graph keeps growing. So all data that's coming in is basically connected without lossless lineage back to the source. And you can do, because the data lakes are meant to be across a lot of data, you're talking about petabyte scale at least. So you're talking about cataloging so that you have a way to kind of meaningfully segment this data. And so all that is part of how you organize your ontologies. And it allows for master data management as well as a side effect. Master data management, if you are from the relational world, it's a big deal. It's a separate project that you have to carve out, and it's a big deal. Of course, it is work involved, but it is fundamentally supported from the ground up. So it makes it easy, and you can really apply your higher level skill and thinking to kind of formulate what you need to do with master data. The other interesting prospect with semantic data lakes, so to speak, is that you have access to linked open data. Linked open data is this wonderful thing, that has been coming out with, a lot of big governments and research organizations have spent billions of dollars doing research in cancer, for example, or weather, and so on and so forth. Put out all the result data onto the web for public consumption. This is at an enormous cost. All that data is accessible. It is all published in RDF, and you are able to leverage that if your systems are in use semantic technology, and that's for free. So if your data lakes are smarter, now you can aspire big. Now you can actually plan on doing the next thing. And the next thing is to actually convert that into a smart analytics platform. And at Lead Semantics, we try to do that. So we use HDFS as the scalable storage layer. And then on top of that, there is an in-memory cache layer that kind of helps you query this at runtime, both for querying purposes as well as when the ingest happens to apply the semantic models kind of before actually striping it onto these HDFS layers. The ingest happens through any platform like Spark, for example. You can run off background jobs using Spark. All input data gets funneled through Spark jobs and applied semantic model, and then it gets added into RDF graphs. And they get striped across this HDFS Hadoop cluster. And you end up with a single query interface. And that gives you a chance to kind of come up with, as I said, BI and visualization, modern BI and visualization tools that can completely navigate the entire lake. Of course, given that if you expect these visualization tools to be running in browser, you have natural limitations in terms of how much they can handle in queries and so on. That you can easily add on. As I said, there are many, many ways to add on these constraints in a systematic way, to the ontologies and so on. And we have come up with a tool called HidDime. HidDime stands for hidden dimension, and it's a analytics interface. It uses Sparkle to go against these lakes. Hopefully I'll run a 2-minute small demo to kind of showcase, being that, as I said, it uses semantic technology, it may be relevant. So with the smart analytics platform, you can do analytics that are driven by the semantic model, which means it gives you a lot more flexibility in terms of what analytics you can do. You can do reasoning and inferencing. Reasoning and inferencing gives you a chance to, add in new data that was not in your source channels, that never existed. But this is consistent data that when you add will give you new insights. And you are perfectly fine in using this new data, and that's all computed through this additional processing called rules and reasoning. And with complex models, you can do all your advanced analytics with the system. So that we strongly believe that empowers the analyst with a single query interface. The analyst can build their purpose, as I discussed earlier. They can build their analytics specific segmentation of the big data lake, bring it out and apply their analytics and do their analysis. And it allows for new age BI and visualization tools. These visualization tools, they can deliver not only the old world operational analytics, they can also deliver this new age analytics as well. So I will take like a minute and a half or so to kind of showcase a small demo of HitDime. In this case, we are trying to showcase an operational analytic, which you may be easily able to relate, being that you can see that in other visualization tools. Like for example, in this case, an e-commerce company, it wants to incentivize each month buyers who directly influenced new purchasers. A buyer has bought in one time, they have influenced other buyers later on, and so they want to incentivize the first buyer. So it reads like this, the find customers who bought Apple products. In this case, we have some data about Apple and so on. In April of 2015, again, we have that data, and tweeted positively whose followers have purchased Apple products post April 15. So that is, you have a causal chain so that you can be sure that we are getting the right thing. So without further ado, I'll just run the demo. Just a minute and a half, if you just will bear with me. This runs in a cloud environment, in the browser. So this is, different data sets are getting selected. You are selecting the different categories, like we said, customers who purchase in a certain period, time period, and Apple products, and so on. So that happens here. All of this, these are like dimensional cube related stuff up front, but that's what I'm trying to say. At the bottom, even though it is an RDF graph, we are able to deliver operational stuff, easily. Being that, this data is across 4 different data sets, you would have to combine these things. And in the case of a RDF graph, you can reach out to any far-flung attribute, from wherever you are, because, it is connected one way or another. So it's easy to kind of, write out your queries to kind of get there. So it is getting all that information. It finishes in some time. It's more than anything, it's just to showcase that, you are able to actually query seemingly tabular data, build your, cubes dynamically. I mean, this cube layer is on top of the graph. The grid layer is on top of the graph. So graph is your final substrate. This is the final graph that shows, all the followers that actually bought. It pulls out that attribute, if you can read, the date is actually, either later part of April or in May. Yeah, I think it closes right here. And it is showing the Sparkle query on the left-hand side as well. So, so just to showcase that, all that interactions, all that was done through interaction, and the equivalent query is on the left-hand side, it's in Sparkle. So with that, I would say thank you, and do I have time for Q&A? I'm sorry. Okay, all right.
HitDime, an innovation revolutionizing numbers and data. You will no longer be detouring, but making dollars out of your data. HitDime makes it easy to explore BI data warehouses by business analysts. A simple yet powerful next-generation BI tool makes analytics very easy and accessible to any person. HitDime provides the flexibility to bring down a minute level of data without running any complex queries or script. It incorporates cognitive thinking and converts big data into smart data using semantic technologies. Any business, manufacturing, retail, e-commerce, mobile wallet, agriculture, health, insurance, with HitDime, your smart data is at your fingertips when triggered by a point and click. A revolution in business intelligence tool, HidDime's dynamic insights substantiates corporate goals and empowers frontline managers and any domain specialists. In making day-to-day decisions, no need for huge investments in IT infrastructure. No IT SQL knowledge required. All you need is a browser. With HidDime, you are your own data analyst, data engineer, and data scientist. Connected graphs, dimensional cubes, pre-canned reports, and all visual analytics are one click away, on cloud, on-premise. Multiple people can work on same data sheets simultaneously, wherever they may be around the world. From dissonance to resonance, HidDime will change the phase of data analytics and revolutionize the way data can be analyzed and improve your business. HidDime, at point and click, connects art of business with science of data.
Thank you so much. We really hope you enjoyed that session by Prasad. If you have any questions, he's welcome to take them offline. I'm sure he'll be more than happy to take your questions. So if you have anything, you can always walk up to him and have it clarified. Thank you so much, Mr. Prasad. With this, we move on to our next session. And the question is, can we reach 1 billion without one S and OS? So we have with us today Juhi Bhatnagar, who's head of analytics at Clover Infotech. She has an experience in various analytic roles in industries across India and abroad. Over the last few years, she has been involved in conceptualizing diverse data science projects and setting up captive analytics divisions for leading organizations in India, UAE and US. When asked about her love for analytics, she says that it began when she published a chapter on white light interferometry during her research internship in Norway. Welcome, Juhi. Let's put our hands together and welcome her this afternoon. I'm sure we can clap louder than this, yeah? Thank you.